Okay, so we begin this course on VLSI signal processing. I had already given a preview of what the course content would be, so I am not getting into that. Straight I will start with the first topic, which is graphical representation of DSP algorithms. We have got three kinds of graphs. One is called signal flow graph, that is SFG. Next is data flow graph, DFG, and third is dependence graph. Of these three, the first one is not very widely used, but then we have to start with this to understand both data flow graph DFG and the dependence graph. Okay. So, we begin our discussion with signal flow graph. By the way, I forgot to mention, you should, for most of my lectures, it is very important that you follow my lectures, because I teach from my own understanding, you won't find normally in books, but still you need a reference. For that, you should look at this book. By Keshav K. Parhi. It is available in Indian edition, Willie Eastern. So, quite a cheap book. This Keshav Parhi has been an ex-student of IIT Kharagpur and has become very famous. He is a very well-known professor at University of Minnesota at Minneapolis. He has come out with this book, and this is a unique book of its kind, because we do not have any other book like this available, which deals with so many types of VLSI architecture optimization techniques for DSP and communications. I mean, so many results are available, but they are all scattered in journals in various forms, but it goes to his credit to compile all of them together and thread them together and come out with a very nice book. Of course, this is not an easy book, this is a very difficult book to read, that is why I come in. If you follow my lectures and also consult the book, then things will be easy. Also, many things I teach which are not in the book at all. So, you have to be very careful to while attending my lectures. Okay, it's very important that you follow my lectures and then you also consult this book. Okay, all right. Signal flow graph. This consists of two items mostly. One is called node. They are denoted by bubble. This indicates, nodes indicate computation or some task, process, whichever way you want to call it, computation. Okay. That is, it does some job. Maybe several jobs, many jobs can be put under one node, or maybe a very simple operation can be put under one node. It is all up to you to decide about what will be a node, what all operations will be within a node, but node is indicated by a bubble. Another is called directed edges, indicated by this. It means it indicates flow of flow of information. I mean, it starts at a node, and ends at a node. Like this. There are two nodes, there can be an edge like this, which means there is a physical connection from this node to this node through a line. But this line, the arrow indicates the direction, that is why it is called directed edge, and this directed edge means information can only come from this node and go up to this node, not in the opposite direction. Okay, so this is one edge, and direction indicates flow of direction. This means a physical connection. There will be a physical connection, a bus or a wire which will take information, data from this node and take it to the other node. All right. Now, in the case of SFG, node edges can also carry out some linear operations. Like constant multiplication. That is, we may have an edge if I by the side of it write k, it will mean whatever information coming out of this node, that will be multiplied by k, and then will reach here. So, if this node produces some sequence xn, what will come here is kxn. Okay. So, this multiplier, which is a linear operation, this we can write by the side of the edge. So, in the case of SFG, edge not only transmits information, but also during that time it can carry out a linear operation like constant multiplication. Remember, when we deal with the other graphs DFG and DG, okay, there also we have nodes and edges like this, absolutely same, but there the edges may not be able to carry out linear operations like this. In the case of SFG, constant multiplication is possible, so you write k by the side of an edge, it will mean k times incoming information that will be given to the this node, destination node. Another operation is delay. Okay, that is, suppose if I have got things like this and I write q times d, d is delay, 1d means 1 clock cycle delay, 2d means 2 clock cycle delay, qd means q clock cycle delay. This will mean if the node generates some sequence xn, this will be delayed by q cycles, and what will come here will be xn minus q. Okay. So, in the case of SFG, you can have edges, directed edges, not only carrying transfer of information, but also you can have constant multiplication or delay, along with the edge. That will be also part of the edge. That is true only of SFG, not true of the other two graphs. Okay. And there is a source node It's like this, a node from which edges only come out. No edge comes to it from any other node. It's like a signal generator, it only generates data, information, signal, and then it goes to other nodes. Like you can have multiple edges going out, but nothing comes in, nothing comes in. Okay, this is a source node. Similarly, you can have a sink node. Here, there can be many incoming edges falling on it, but nothing goes out, nothing goes out. That is called sink node. So, there is a terminating nodes, both are terminal nodes, one is the beginning and the end, all right. At time when I give you a problem like a DSP algorithm and I ask you to draw a signal flow graph or DG or dependence graph or data flow graph, one thing I must make clear at this stage, there is nothing unique. There is nothing unique about the graph. The graph depends on you. I mean, what all operations you are putting in a node and how are the nodes getting connected, it all depends on your choice. Of course, we would stick to certain choices because they are optimal, but again I tell you there is nothing unique about it. It depends on who is drawing the graph, how he perceives, all right. So, with this I take an example. FIR filter. Suppose you have got yn is the filter output, b0 times xn, b0 is first coefficient, then b1 times xn minus 1, then b2 times xn minus 2 and b3 times xn minus 3. Just 4 coefficient, third order, because if you take Z transform you will have up to Z to the power minus 3 from this last term, that is a third order filter or equivalently 4 terms, 4 multipliers. I want to draw a DG. So, obviously, SFG, signal flow graph. So, I will have a source node that will be generating xn, okay. Then again I tell you it all depends on how you draw, it depends on the person. I am drawing, so I will draw in a particular way. I will have a node here, this node is called splitter node. What it does is this, it takes the incoming data and gives it out in 2 directions. So, same xn comes out in this direction also, this direction also, okay. So, it splits. Then by the side of it is an edge, I can have a multiplier or a delay or both. So, I write B0. Then I have another node. Normally, these two can be different nodes, but we just indicate them by bubbles or circles. But then one can ask the question that how do I know what kind of node it is and what kind of node this is. Just to see that you are not confused, I put a plus here to indicate it is an adder node. Adder means it takes 2 input, 1 output, that is an adder. So, this is 1 input, another one I give 0. So, this is an edge, okay. Then a splitter, and here I put 1 cycle delay, 1 into D, 1 cycle delay. Then again a splitter node, it will split the same thing in 2 directions. This edge, sorry, again a plus. So, this edge, this signal gets multiplied by B1, this signal gets multiplied by B0, okay, again an adder. This goes to a splitter. I will tell you what we are doing actually, but by the side of this edge I give 1 cycle delay, so 1D which is D. Again this splitter, it splits this signal into 2 edges, a splitter node, so it splits it into 2 directions, one is this direction, there is again an adder node, and I give a multiplier with this B2 and this goes to another node. I give 1 cycle delay on this, this goes this way, this is another edge, these edges are free, now no multiplier with them, no delay with them, but node to node. I B3 with this and this is sync node. So what is happening, you see, xn is going here. It is getting split into two directions. This is coming as xn multiplied by b0. So you have b0 xn plus 0. So I have b0 xn here, b0 xn. This is getting delayed by one cycle. So I have got b0 xn here. Now xn coming out of this node in this direction also, because this is a splitter node, that is getting delayed by one cycle. So xn minus 1. This is again a splitter node, this will come in this direction multiplied by b1 added with this. So I have got, and they together the summation moves, xn minus 1 is further delayed in this direction, xn minus 2 gets split into two directions. This way it is gets multiplied by b2, gets added with this. So b2 xn minus 2, and this gets further delayed by one cycle, so it becomes xn minus 3, it comes to this direction, b3 xn minus 3 gets added with this. This is my output, and clearly this is the yn. Okay, so this is a simple SFG. The sync node, source node, I don't have to do anything with this. If I want to have more and more stages, this will get continued. Okay. Now one thing we have to calculate. Suppose adders, we have got two types of jobs here. There are four multipliers in parallel. Along the edge, I have B0, B1, B2, B3. They are working in parallel. B0 multiplies the incoming data here, B1 multiplies the incoming data coming from this node, B2 multiplies the incoming data, B3. Okay. So suppose multipliers it takes time Tm, maybe Tm microsecond or picosecond or nanosecond, whatever is the unit you deploy. I write u dot t dot, unit of time. Okay, Tm unit of time. And then I have got adders. Splitters don't take any time. Whatever is coming, you are just passing it in two directions. Okay, so that doesn't require any time. But multiplications, yes, they take a lot of time. In VLSI design, multipliers are the big headaches, because when you multiply say to 32-bit numbers, you have got 32 by 32 array, shift and add, shift and add, shift and add, go on doing it 32 times, 31 times. Okay, so that requires lot of time, lot of hardware. That is why multipliers are the biggest concern in VLSI. For VLSI designers, we try to either minimize multiplication complexities or get rid of multipliers altogether if possible. Same is not for adder. Adders are much simpler. So adder, the time, I call it TA unit of time. Again, TA microsecond, millisecond, I mean nanosecond, picosecond, whatever is the time involved. Okay. Obviously, Tm much greater than TA, because multipliers take much more time than adders. The question that you ask is this: if I give an input xn, how much time will be required to generate yn before I can give next data? Because I have to give this entire circuit some time to compute the job, that is to compute yn. Then only I should give the next one, right? How much time? Now you see, as I told you, splitters, they don't take any time. So here I have got four multipliers in parallel, B0, B1, B2, B3. So they are working in parallel means they occupy the same time. During the same time, four are working parallelly. So I will have Tm, but how about the adders? Adders have a problem. This adder takes TA amount of time, but it adds this guy and this guy. But this guy is not available unless this adder completes the job of addition, then only this is available. So before this TA, another TA amount of time needs to be employed here to compute this addition. And again, this can be obtained only if this addition is over. So another TA amount of time needs to be dedicated to do this job before I go to this. And again, this requires this, which is obtained from this addition. So I need another TA amount of time. So total, I need 4 TA. This is the amount of time. If I have got, instead of 4, I have got 400 terms, I would have had Tm plus 400 TA. Multipliers are working parallelly, so Tm remains Tm, but all the adders you see, they are sequential. One adder output goes to the input of the other adder. So first I have to complete the job, then I go here. Then again, this goes to the input of the other adder. That is, then I have to complete this, then only the next adder can start its operation, so on and so forth. So, the adders are sequentially connected here, one after another, that is why all the times get added. Now, I will show some transformation technique by which this given architecture will be changed to transform to another architecture, which is equivalent. That is where if I give the same input x n, I would get the same output y n. But there we will see the time required to compute y n for an x n will be lesser than this, which means that circuit will be faster. It can handle data at faster rate because its own computation time, overall computation time will be less than this. That is called transpose form. That is, we obtain by a technique called transposition. So, there are very high level transformation techniques that given a graphical description, you can apply one of the transformation techniques, get something which is equivalent to this in terms of the input output relation, but then that equivalent circuit may have a better feature than this, maybe in terms of speed, maybe in terms of total computation and hardware or chip area and so on. So, in the case of signal processing graph, there is one technique called transposition. In the next class, in the next half, I will discuss transposition of SFDs. Okay. We are given a SFG, we make the following changes. I wonder whether we can do it in the next class or maybe we continue here. You reverse the arrows. If there is an arrow pointing in one edge, keep the edge in the same place, but reverse the direction in the SFG. Number 2, splitter node, change it to adder, and adder change it to splitter. Okay. Source and sink, interchange them. Okay, source and sink. And lastly, delays and multipliers in the same place, do not disturb. Okay. If we apply these techniques to a SFG, then you get a transposed form. Okay. Then you get a transposed from this SFG. All right. We will apply these techniques to that SFG of FIR filter we have obtained a while ago. So, I once again draw that SFG. So, we had that this time, source, okay, I will once I draw this, I will stop now and then I will take it up in the next class. We had already drawn it, but for comparison purpose I have to still draw it again. So, I had already drawn it last time and it goes to source sink node, all right, B0, B1, B2, B3 and this. And time taken was, as I found that time, Tm plus 4 Ta. This much time was taken. Now, we will be applying transposition to this circuit and we will get an equivalent form. We will first see that the one which you get by applying transposition is indeed equivalent to this. That is, if I give xn and get yn here, in the transform circuit also if I give xn at the input, I will get back yn. And then I will try to calculate the time taken by the circuit to produce the output yn for a given xn. At that time we will see it will be less than this, which means as far as speed is concerned that will be faster, more preferable. But that will have its other demerits also, that also we will discuss. So, that is all for this class. We will move to the next class and there we will discuss this. Thank you.